Good afternoon, everyone. You're in for a treat because we are about to hear from a dynamic young physicist from Harvard. Her name is Diana Prado Lopes Aude Craik, and she is originally from Brazil. She came to Boston to study at MIT. Then she went to England to get her PhD from Oxford University, and then came back to Boston to continue her research as a postdoctoral fellow at Harvard. And we are so glad that she's here to share with us her extraordinary experiences trapping individual atoms for quantum computing. So please help me welcome to the stage Dr. Diana Aude Craik.
Thanks very much. Okay, I'm going to tell you guys today about how to trap single atoms for quantum computing. Okay, so I'm going to start off by showing you a photograph that was taken with a regular camera. And that little purple blob that you see in the middle there is a single atom. Okay. Now you may be thinking, hang on a minute, a single atom is tiny. Can you really photograph it with just a regular camera? Well, actually what you're seeing there is not the atom per se. It is the fluorescence, the light emitted by the atom when I shine a laser on it. So when I shine a laser on this atom, it sort of glows. And this glow can actually be captured by a camera. And the first time I saw the glow from a single atom like that, just suspended in a point in space, I was really, really amazed. Because everything around us is atoms, right? I mean, the air is full of nitrogen atoms, oxygen atoms, we're made of atoms. I mean, how do you isolate a single one, stop it like that, and then just look at it emitting light? So I'm gonna tell you about the recipe for how to do this, which I learned in grad school. And first of all, let's start with the ingredients that you need to trap an atom. Okay, so first of all, what you need is a bunch of atoms. So we have to first choose which type of atom we'd like to trap. I'm going to choose calcium atoms. And this is a bunch of little blobs of calcium atoms in a test tube that has had all of the oxygen removed from it, which is why it looks a little bit silver and shiny. And you might expect calcium to look white because there's a lot of calcium in milk, for instance, and your milk is white. But that white only comes when you take it out into the air and it can react with oxygen. So that's why it looks shiny over there without oxygen. Okay, so we've got the atom that we would like to trap. We also need some kind of device that traps the atom. And this type of device is called an ion trap. We'll learn about why it's an ion trap and not an atom trap a little bit later on. But this device here, if we just zoom out a little bit, it looks a little bit like a computer chip, right? And it's gold. The electrodes in the middle there are gold. And this one actually happens to be the one that I made during my PhD. Okay, so we've got atoms, we've got the device that is going to trap the atoms, but how am I going to trap a single atom of calcium with this device in air? That's not going to work, right? Because if I try to put this thing in air, what's going to happen is all of the atoms around are going to bump into my calcium atom, push it around and knock it out of the trap. So what I have to do is take this ion trap and put it in what's called an ultra-high vacuum system. And this is just a metal can, okay, and it's got a window, the circular window there, which is why you can see the ion trap in there. But basically it's a closed metal can, and it's connected to some very powerful pumps that just suck out all of the air from inside there. And to give you an idea of how little air, how little gas there is in there, the pressure in there is basically the same as the pressure on the moon. Okay, so we put our trap in vacuum, and we take those calcium atoms that we looked at in the beginning, and we actually put them in a little metallic tube, which if you squint, you can see over there. And that little metallic tube we call the calcium oven. Why is it an oven? It doesn't really look like an oven, right? Well, it's an oven because we actually run an electrical current through it that we apply from outside of the vacuum system, and that electrical current heats up the calcium that's inside, just like an oven would. And when the calcium heats up, it evaporates into a gas, and it gets sprayed over my ion trap. Okay, there's one more ingredient we need to trap these atoms, and that's lasers. And that's all we need. So I'm going to tell you how, using these ingredients, we're going to trap a single calcium atom. And to figure that out, we first need to look at what an atom looks like inside. And for the calcium atom, we actually have 20 positively charged protons in the nucleus. and an equal number, 20, negative electrons swishing around the nucleus. Okay. Now, the total charge of this atom then is plus 20 from the protons in the nucleus, minus 20 from the electrons, so it's 0. It's what we call a neutral atom. There's no charge, right? So let's just for fun draw all of those 20 electrons on here. And now I want you to focus just on the very outer ones, the ones that are furthest away from the nucleus. So I'm going to hide all of the inner ones. They're still there, I'm just not drawing them. And now I'm going to tell you that if I shine a purple or blue laser onto this calcium atom, I can actually kick out one of these outer electrons, get rid of it. Now the atom has one fewer electron, so it actually has a positive charge. And when an atom is charged, we call it an ion. Okay. So this is a calcium ion. Right, so how does that help us? Well, it's very important that the atom is charged, because if you have a charged thing, you can actually use other charges to push it around, right? And if we can push the atom around with other charges, we can maybe confine it to one point in space. So let's see how that works. First, let's remember that if I have two opposite charges, a positive one and a negative one, what happens? They actually attract each other, right? And if I have charges that are the same, what happens is the opposite. They don't like to be next to each other. They repel, right? So using these forces of attraction and repulsion, I'm going to trap this ion. Now, how might we do this? Well, if we're going to apply all of these charges around the ion, first of all, we remember that it's positive. We better have something to apply the charges to, right? And what that something is just a bunch of metallic electrodes that we can apply voltages to and charge up. Okay, let's put two pointy electrodes on here. And these electrodes, these pointy ones, we nowadays call the Endcap electrodes. And okay, let's put some more electrodes on. Let's put two big ones here, and another two the other way around. And basically now we've surrounded the ion with electrodes. And these big flat ones we call the blade electrodes, because they kind of look like part of the blade of a knife. And you might recognize this. If I look at this electrode geometry sideways on, it's actually that picture that I showed you right at the beginning of the talk. So the pointy electrodes are there, the Endcap electrodes there. Above and below the ion, you see the blade electrodes, two of the blade electrodes, and the ion in the middle. Okay, so if I zoom in here first, my ion is positive, right? So I want to keep it in the middle. So one thing I can think of doing is I can make those two Endcap electrodes positive too. So it won't want to go towards one, it won't want to go towards the other, it will just stay in the middle, right? Well, yeah, but it can still kind of escape up and down through those blade electrodes, right? So we have to do something with the blade electrodes too. So one thing we could think of is we already made these Endcap ones positive. So maybe I can make this one positive, 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 and now it's all positive, it doesn't want to go near any of them, it'll just stay in the middle, right? Well, unfortunately, that doesn't work. That configuration of charges is unstable, and if you do that, the ion was always going to find some way of wriggling out and escaping the trap. Okay? So you actually have to do something a little bit fancier, and here's how it goes. What you do is, the Endcaps are still positive, I make two of my blade electrodes positive, but I make the other two negative. And now you think, okay, hang on a minute, but negative attracts the positive ion, right? Yeah. And if the ion isn't right in the middle of the trap, it's probably going to get attracted to the nearest negative blade, right? Yeah. And if it gets attracted to that, it's just going to hit that, and that's no good. So what we do is we don't keep it like that. We flip the charges around so that the blades that were positive now become negative, and now they push the ion away, okay? And now I flip it again. And now the ion gets pushed to the other side again, and it's just moving back and forth like that, right? And now I want you to do a little bit of a jump and think about the ion now as a marble, and think about the positive electrodes as hills, because the marble doesn't want to go up the hill, okay? And think about the negative electrodes as valleys. The marble wants to go towards the negative electrodes down the valley, okay? And if you think about it like that, you can actually visualize exactly what this configuration of charges looks like to the ion. And it looks like this. It looks like a flipping saddle, okay? The positive electrodes are the hills, the negative electrodes are the valleys, and you flip the charges so it goes up and down. And if you flip the saddle quickly enough, then the ion can't escape. So that's the basic principle of operation of an ion trap. Okay, great. So let's just zoom out from that picture of the single ion. And this is a regular ion trap that has that geometry that we've been talking about that whole time, okay? And the size of this, if you're wondering, is about a ping pong ball. But what about that little gold chip that I showed you at the start, and I told you that was an ion trap? That looks nothing like that, right? Yeah, so that's actually quite exciting, because about a decade ago, scientists figure out that you actually don't have to surround the ion with electrodes. What you can do is you can take those electrodes, you can project them onto a plane, you can put them all on a flat surface, like the surface of a chip. Okay? And actually, if you apply a similar configuration of charges to those flat electrodes, just above the surface of that chip, you can still trap the ion. And when I say just above, it's about the diameter of a hair above the chip, 100 microns above the chip. And that's really exciting because these chips are much smaller, first of all, about the size of a dime, and you can fabricate them very easily, just like you make computer chips. You can basically stamp them out, print them out, make loads of them, and make many electrodes on a single chip, so that instead of just making one ion trap, you can make many on a little piece of gold like that, okay? So let me just show you, if you zoomed in to some ions trapped in the center region above this chip, you would see something like this, a string of 4 ions, say, trapped there. All right, so now we've trapped an atom. That's very cool and all, right? But what can we do with it? We can actually use these single atoms to build the basic building blocks of a quantum computer. But first, before I explain to you how we can build a quantum computer with atoms, we first need to understand how we build a regular computer. Now, okay, a regular computer, we're used to talking about how computers store information in zeros and ones. And what that means is just that the computer can represent any information you would like to represent as a string of zeros and ones. So for instance, if I want to write down a number, I can represent it as a string of zeros and ones. 1 through 4 is up there on the board. I can also represent a letter as a string of zeros and ones, using a code that translates the letter to a string of 8 of these zeros and ones, called ASCII. I can write the letter A like that. And, at the start of the talk, you might have noticed that my name is quite long. People often tell me this. But in binary, it's even longer. It's that long. And one of these zeros and ones is actually what we call a binary digit, which, if I abbreviate, might remind you of something you have heard of a lot, a bit. And this is 1 unit of information for a normal computer. Okay, so these bits, these 0 and 1s, what are they? What are they physically, right? Well, they're actually switches. And the way we implement these switches in our normal computers is we use what's called a transistor. A transistor is just a switch. It looks a bit like that weird thing over there that has 3 wires coming out. And that one over there is off. And so we say when it's off, it's representing a 0. To turn it on, all you have to do is apply a little bit of electrical charge to that middle wire over there to turn the switch on. And when it's on, we say it's representing a 1. Okay. Turns out that if you know how to store your information in bits, if you know how to flip the bit between 0 and 1, which we just talked about, it's just changing the switch from on to off, you only need one more ingredient, really, to be able to do any type of calculation you would like on your computer, and that ingredient is a logic gate. It's a logic gate. Well, a logic gate is basically a little machine. It takes in 2 bits, the state of 2 bits, and I'll label these 2 as input A and input B, and it outputs another bit, an output bit, okay? Okay. Now, these gates in normal computing are actually very aptly named. Their names are very informative. So I'm going to show you an example gate, which is the AND gate. And the AND gate, the way it works is very simple. The output is only 1 if both input A and input B are 1. If they're anything else, the output is 0. Okay? And just to go through how it works, okay, say input A and input B are 0, I get 0 out. If one of them is 1, the other one of them is 0, I get 0 out. But if both of them are 1, I get 1 out. Okay, so basically it's just a little machine that, depending on what the input states of the 2 bits are, I get a different output state. And just with a logic gate and with the ability to flip the bit, you can do any calculation you might want to do on your computer. It's very simple. Right, so we know how to make a normal computer. What's the big difference between that and a quantum computer? Well, this bit that we've been talking about in the regular computer can only ever be in one of 2 states. It can either be 0 or it can be 1. But a quantum bit has this funky property of being able to kind of be 0 and 1 at the same time. It's actually what's called quantum superposition. The state of the quantum bit can be in a superposition of 0 and 1 at the same time. Okay, but why is that useful? Well, to see why that's useful, let's think about having 8 bits, 8 normal bits. We usually call that a byte. Okay. Now, how many states can this byte store at a given time? Well, there are 2 to the power of 8 possible configurations of this byte. Okay. But at any given time, it can only be in one state. Okay? What's the state that it's in right now? Well, it's storing 1, 1, 0, 1, 0, 1, 0, 0. That's what it's in. Okay, what about if I have more bits? Well, say I have 80 bits. Well, that's got 2 to the 80 possible configurations, but again, at any given time, the number of states it's storing is 1. Okay? Now let's make these 80 bits into quantum bits. Well, if I have 80 quantum bits, then at any given time, I can actually have them all in a superposition of all possible 2 to the 80 states. And how big is 2 to the 80? Well, it's that big, but that doesn't tell you much, right? To give you an idea of how big it is bigger than the number of atoms in the observable universe. So if we think about this for a second, if I take every single atom in the observable universe and I make that into a regular computer bit, I couldn't store as much information with those bits as I can store with 80 quantum bits. Now that sounds pretty good, but after all of this, I still haven't told you how I can make quantum bits with the trapped atoms, right? So let's get to that now. Okay, so to see how I can make a quantum bit with the atom, I need to take you back to what that atom looks like inside. So remember that we had kicked out one of the outer electrons with the laser, and so we left that poor lonely one out there, the single outer electron there. So if we just think about that extra electron for a second, it's got an extra property that I haven't told you about yet, called spin. Now, one way you can think about spin is you can think about the electron as being also like a little bar magnet. Okay? And this bar magnet can point up, north-south, and when it does, I'm going to say that the ion is storing a 1, or it can point down. And when it's pointing down, I'm going to say the ion is storing a 0. And to go between 0 and 1, what I can do is actually apply some microwaves, just blast my ion with a little bit of microwave radiation, and that microwave radiation actually rotates that spin, that little magnet that the electron is associated with. And the length of time that I leave my microwaves on for is what determines how far that magnet rotates. So I can leave those microwaves on to rotate from 0 to 1, so flip completely the magnet, or I can actually go anywhere in between. And if I stop somewhere in between, that's a superposition. Okay? Right. So now, just like in a regular computer, we have a bit, actually a qubit now, and we know how to flip it between 0 and 1. So there's one more ingredient, if you'll remember, that we need to do computation. It's just like in a regular computer. We need the bit, we need to flip it, and we need to do gates. Right? So how do we do gates? To do gates, we're going to use that same little magnet property of the electron. But I have to tell you a little bit more about how that little magnet actually affects how the ion moves in space. So it turns out that if I have my ion and it's in the state 0 and the magnet is pointing down, and I apply some magnetic field around my ion, and this magnetic field looks basically like a hill. It goes from low magnetic field over there on that side of the board to high magnetic field on this side here. Okay? It turns out that if my ion is in this state where the bar magnet is pointing down, it wants to go to the area of low magnetic field. It likes to go down the hill. Okay? However, if I flip the magnet, the electron's magnet, the spin, it wants to go the opposite way. It actually wants to go up the hill. You can kind of think of this as if you flip that electron spin, it's kind of like you flip the world for it, and it wants to go up instead of down. Okay? Right, so how is this useful? Well, let's say that now, instead of making a hill of magnetic field, I make a bowl of magnetic field. So I have low field in the middle, and I have high field on the edges, and I put 2 ions in that field. Okay? Now, they are both pointing down. South is on the top. So what do they want to do? They want to go to the point of low field. They both want to go to the point of low field. So what's going to happen in this scenario is they're going to move that way. Okay? Now what happens if I flip the bowl? Well, now low field is that way. So now they want to go the opposite way. Okay. So what about if I flip it again and I just keep flipping it? Well, now I'll excite a motion that's like this. Okay. And if you want to see what this actually looks like with 4 ions in a trap, it looks like that. Okay. Now I have to give you a caveat here that this isn't exactly the motion I'm describing. It's a very technical caveat, but I have to give it to you anyway. But it looks very similar to that. Okay. Right. So based on what the qubit state of my ions was, they moved a certain way in the trap. I just want you to keep that in mind. Okay. Now let me show you what would happen if I flip the state of one of my qubits. Well, the one that's flipped now likes to go to high field instead of low field, right? So actually, that one is going to go that way, and that one with south on the top is going to go that way too, to the point of low field. So they are now both going to move like this. And when I flip the field, they're going to go that way. And so the type of motion I'm going to excite, instead of this one, which is what we saw before, is this one. And let's look at what that looks like with ions. Looks like that. Okay. So this is actually very powerful, because depending on what the qubit state of my ions was, I have created a different motion in the trap. Okay, so we're going to use that to do gates, but I have one more piece of information that I need to give you to complete the cycle and explain to you how we're going to do this gate. And to do that, we actually need to go back to classical physics a little bit, and we're now going to think of the ions as just masses on springs. Okay? And I'm going to tell you that this system is very analogous to the 2 ions in that bowl. Okay? And you can think of these 2 masses as the 2 ions. Now, I'm going to show you some videos of somebody exciting both this mode and this mode on that spring. So the top one, he's exciting this mode. The bottom one, he's exciting this mode. Okay. And there are 2 things, if I slow the videos down, that I want you to note about these videos. The first one is that to get the ions moving, or the masses in this case moving, all the person had to do was push it once and release. And then there was some kind of natural oscillation going on. Okay. The second thing is that oscillation is interesting, first of all, because it happens by itself. Once you push it once, it just happens, okay? And it happens at a sort of natural rate, at a sort of natural speed, you know? And this is just like if you go to a park and you go onto a swing and you ask your friend to push you. If they push you, that swing also has a natural frequency. And if they push you at the wrong rate, they don't push you like alongside at the same rate as the swing wants to move, you're actually not going to move very well, and the swing is eventually going to stop. But if you move in phase with the way the swing naturally wants to go, you can get that swing to move really far, right? So it's the same thing here. It's really, really hard to see this in these videos, but it turns out that the natural speed at which this one happens is faster than the one at which this one happens. So this one goes a little bit faster than this one. Okay. Because there is a difference in rate at which this happens and at which this happens, by choosing how fast I flip that field that makes the ions move, I can choose which one of these motions I excite. Make sense? I just make the rate at which I flip up to down equal to the rate that, for instance, the ions like to naturally move like this. Okay? And that's exactly what I'm going to do the gate. It's called a motional gate, funnily enough, because it's all about motion. And if I put in 2 qubits, one pointing up and the other one pointing down, you will remember that in that configuration, they wanted to go this way, okay? But I'm not going to flip the field at the rate that is correct to drive this one. I'm going to flip it at the rate that is correct to drive this one. So what happens if my input states are 1 and 0 or 0 and 1 is nothing. I will see exactly the same output with no motion. However, if I then flip one of the bits, and they are now both either 0, 0 or 1, 1, you will remember that if they were the same, they moved like this, right? And I am now changing my magnetic field at the rate that this likes to move. So now, what I see is motion. And this, I can tell you, is a gate. Why? Because depending on what the input state of my qubits was, I get a different thing happening, a different output state. So this is the final ingredient you needed to be able to do any operation you would like to do in a quantum computer. You have your gate, you have the ability to flip your qubit, and that's it. Okay, now just to finish, I wanted to tell you that ions, trapped atoms, are actually a very exciting candidate for making quantum computers that are very large scale, because they can actually stay in those quantum superpositions for a very, very long time, comparatively. The second thing that's cool about them is that you can do this type of operation, this type of gate, with extremely high precision, which means that you can do many of these gates without making many mistakes. And this is essential if you're going to do very complicated, long computations, because if you're going to get something that makes sense out of your calculation, you need to not make mistakes very often, right? And the last thing I want to tell you is that quantum computing is really exciting, not just because of what you might have heard, like, you might have heard that there are certain problems, very specific problems, that quantum computers can solve much faster than a classical computer, like, for instance, factoring very large prime numbers. But for me, what really excited me about quantum computers when I first saw this field, first learned about it, was that nature, in its most basic building blocks, is quantum. So if you want to exactly simulate any process in nature, you need a quantum simulator, right? For instance, if you would like to design some new medicines, you need to understand how a protein folds. And this is very complicated, but it can be done with quantum simulation. You can even simulate things that you could never imagine would be possible to do experiments in the lab, like, for instance, a black hole. You can simulate that with a quantum simulator. So that's why I find this field extremely exciting. And I want to thank some collaborators here, and to thank you very much for coming and listening to the talk.